All right, today we're going to cover section 6, applied optimization. What does that mean? What is an optimization? What does it mean to be optimization? What does it think that refers to? What does to optimize mean? In one way, yes. Yes, and we're going to look at it that way. If we make it more efficient. In other words, if you're a business, you want to try to make as much as you can material-wise as spending the least amount of money. If you're a physicist, you want to make sure that you have the most amount of energy yield with least amount of material being used. If you're a shipping organization like Amazon, you want to know what's the perfect size box to minimize waste of material. So these are all optimization. So you're looking at the most of something or the least of something, which are we call extremas. That's what we did. That's why derivatives are important here. The first derivative will tell us if it's maximum, minimum, the highest, lowest. But what do you think the second derivative would be useful for in this case? What is second derivative really used for? How do you mean?
Finding like the X and Y value. Like where it starts going
Increase, decreasing is first derivative. What does second derivative find for us? Concavity, right? So if it's concave up, what is that going to tell us? Yes, the second derivative is positive in that domain, in that area. But what does it tell us? What can we find with if it's concave up? What can we find for sure? Minimum. We can find extrema. Let's just be a safe point there. Yeah, if it's concave up, then we know that there's a minimum there. If it's concave down, then we know we have a maximum there. And we go back to the first derivative and find those locations. And we know then from there we can compare them all and see if it's an absolute or not. So that's what this whole thing is about here. And we're going to find the same thing here is if it's bounded, then we have to use the endpoints and then find any extrema points in the middle. And then compare them all to see if it's a maximum or minimum. So here we can use derivatives to solve a variety of optimization problems in math, physics, chemistry, economics, anything that deals with looking at extreme values. The best or the least, the most or the least. This is just a very short list of them. There are a whole bunch of other ones. In kinesthetics, or if you look in sports, how can we get the most yardage? How can we design a bat that has the most velocity and impact with lowest vibration? Well, which bat or let's say football that when kicked or thrown, it'll have the furthest distance traveled. All this stuff are optimization problems. Steps to solve these things because these are word problems. Because they're word problems, we have to read them. So the first thing you have to do is read and understand the problem. What is it giving you? What is it asking for? I mean, what can you get out of there? Is all the material given in the sentence, in the paragraph, is it important? Extrapolate what you need, throw away what you don't. Once you do that, if you can draw a picture of what you just read, that means you have a better understanding of what's going on. Because when you draw a picture, it's more just draw a picture, then you start labeling things. Like remember we did the free falling rock that was just dropped because of the explosion. We know at the very top the time is zero, the velocity is zero, but once it starts falling, it picks up speed, and that's kind of stuff. We start labeling these things at certain intervals. Step 3. Identify and define the variables. Because these are physics type problems, physics-esque type problems, things move, things change. And when they change, that's what they call those are the variables. So everything changes with respect to time. If it's a moving problem, if it's a growth problem, same thing with time. So is the population growing? Is it decaying, or what? So identify and label and define the variables that you're using. Define the equation that connect the unknowns with the goal of the problem. Because this is where you integrate your variables into some sort of calculation process. Solve for the unknown variables if you have most of them. And then test these solution ones. Those are your critical values. Test your critical values for what you're searching for. That includes making sure your values that you're using are within the domain of the parameters that you're defining. Yeah, and along the way, you have to define the parameters of your experiment. What does that mean? Is what is a time restraint? Is there a time, or is there a size restraint, a cost restraint, or whatever? We have to know those as well. All right, so let's look at our first example. Example 1, it says, an open top box is to be made by cutting small congruent squares from the corners of a 12 by 12-inch sheet of tin. And the sides are created by bending up the cut edges of the sheet of tin. So, how large should the squares be that are cut from the corners? To make the box hold as much as possible. Okay. So the first sentence, the first part of it, an open top box is to be made. So an open top box. This is what an open top box looks like to me. Is to be made by cutting congruent. What does congruent mean? Same. So this box has to come from a square piece of tin that is 12 inches by 12 inches wide. And congruent squares are to be cut from that corner, each corner. And from there, the sides are folded up to create that box. So how large should these squares be to make the box hold as much as possible? So is this an optimization problem? If so, what's the optimization? Right. We're looking for the greatest, the most volume of this box. So what we're looking for is how big should these cuts be on each of these corners? Since they're square, they have to have the same cuts. So what's the formula for volume of a box? Length times width times height. But if you think about it, what is length times width? That's the area. So basically the volume is the area of a square times the height. Because we want the area of the box that's remaining after we fold up the sides to be that's the part that's going to change. So what do we know? What's the height going to be? We know what the height's going to be. Can you guess what it is? When you fold these pieces in, how tall would the walls be? X. Because that's how length it is here. If we fold it up, it's 8x units high. Okay, so now we got to figure out the since length times width, they're the same size. It's going to be length squared because they're both the same. It's a square sheet. So we're making a square box practically. So what would be the dimensions of this piece of tin that we cut? The overall length is 12, right? But what do we have to get rid of on each side? Here's the length. We have to cut how much? X and X. So we have to cut 2x from both sides. So the area is 12 minus 2x squared. So far, so good.
Why are you squaring the 12 minus 2x?
Because that's what this side is. And this other side is going to be the same thing because it has to be a square. So the length, this is length, this is width. Length times width, since they're the same thing, I can go ahead and square it because the length equals the width.
Okay, thank you.
So we have area times height is the volume. The height is x, and the area is 12 minus 2x squared. And we're looking for the maximum area. We have to define also our domain. What parameters, what's the smallest we can have for x and what's the largest we can have for x? What's the domain of x? Looking at this equation here, this is our volume. What's the smallest it can be? Well, if we set both of these equal to 0, x equals 0, and then 12 equals 2x, so x equals 6. So the domain of this thing has to be between 0 and 6. We need to know that because when we finish because we'll also remember to find the true maximum minima, since we have endpoints, we have to check the volume of those also. Now, when we finish finding the optimization problem, the values we get has to sit inside that domain. Now, how do I find that? To find the optimal size X, what do we need to do? How do we find the optimal? Nope. On the derivative, because the derivative is where we find the vertex, the vertices, which are the maximum minima. We need v prime or dv dx. So dv dx. We have a couple ways we can do it. We can either try to do the product rule and simplify it, or we can go ahead and multiply these out and get a quadratic equation or cubic equation and take each term separately. We get the same answer both ways. Which way do you think is going to be less work? All right, let's try product rule. Okay. So f is x and g is 12 minus 2x squared. F prime is 1. G prime is 2. 12 minus 2x times negative 2, which is negative 4. 12 minus 2x. So we get 12 minus 2x squared plus x times negative 4, 12 minus 2x. So it's 4x, 12 minus 2x. Either way, we're going to have to FOIL this first one out anyway. Or do. Let's see here. We know we can factor out a 12 minus 2x out of both of those. That'll leave us with 12 minus 2x minus 4x. Minus 6x. Okay, so now what do we do? After we find our first derivative, what do we do now? We're looking for the maximum minimum. So what do we do? Set it equal to 0. Because where the slope is equal to 0 is where the maximum minimum is going to be. So we have 12 minus 2x equals 0, 12 minus 6x equals 0. So x equals 6 and x equals 2. All right. What does that tell us? This is now our maximum minimum. These are our extreme points. Is there anything we can't use? Well, our domain is from 0 to 6. Remember, whenever you check the optimal values for extrema, you have to check 3 points. A, B, and wherever you get the interior point. X equals 6 is already an exterior point. It's a boundary point. So we can't use that. What we're looking for here with this equation, we're looking for interior points. Since we know area of bounds. So do we have our 3 points? What we have is x equals 0, x equals 2, and x equals 6. These are the endpoints and the interior point. Where do we plug those? How do we find the location of the extrema points? Right. To find the location of the extrema points, we plug the x values into the original formula, which is v of x is equal to, where's that? V of x equals x 12 minus 2x squared. All right, we kind of know, looking at this equation, what can you tell me about the shape of it? What's the degree? 3. This degree is 1. The multiplicity is 1. That's 2. Add them together, you get 3. So we're going to have a function that looks like this, or a function that looks like this. Is it positive or negative? You sure? How do you know? We don't have a leading coefficient. This is not the leading term. The leading term would be the biggest exponent. We have to multiply these out first. When you do that, let's look at this. Twelve times 12 is 144. Negative, positive is negative. 12 times 2 is 24x minus 24x plus 4x squared. Twenty-four is 48x. Distribute, we get 4x cubed minus 48x squared plus 144x. Now, we didn't need to do this. I just did this so we can see whether it's increasing or decreasing. It's a cubic function. Now we know it's positive. What's our y-intercept? Since there's no constant, it's 0. So we know our graph has a y-intercept there. Does it have another y-intercept? Six, yeah, because you go back to here, this one said equals 0, you get 0, this one gets 6, so we got another y-intercept that's 6. And you know, since it's positive, it's an increasing function. Since the degree of the first one, it's odd. Since the degree is odd, these are multiplicities. Since it's odd, we know this one crosses. Since this one is even, it bounces. So that's what your graph looks like. So we know at 0 and 6, we're going to get 0 as an answer. So at v of 0 and v of 6, they're both going to equal 0 because those are on the x-axis. And we're guessing that at v of 2, let me get you there, we'll have 2 times 12 minus 2 times 2 squared. 12 minus 4 squared. 12 minus 4 is 8. 2 times 64 is 128. So what do we know? Our maximum is what? The maximum volume of this box is 128. When x equals 2 inches or whatever units we're using. So in our box, these are all going to be 2-inch snips. So how wide is the box going to be? So what's our box going to look like? What are the dimensions of our box? All right, let's look at the next one. Example 2. You've been asked to design a 1-liter can shaped like a right circular cylinder what dimensions will use the least material? We know it's optimization because it's asking for the least. You're asked to design a 1 liter can shaped in the right circular cylinder. What does that mean? Right circular cylinder. What's a circular cylinder going to look like? What's a cylinder? A tube. It's exactly what it is. A can, a tube, a Coke can, or a Pringles jar. So we know since it's circular, it has to look like this. Now, where does the word right come from? If you were to look at the can sideways, the angles have to be 90 degrees. That's what it means. It's a right angle circular cylinder. So each of these angles from the side is a 90 degrees. And it's got to be 1 liter. Are we looking for the inside or the outside? Because there you have another question to look at. What exactly are you designing? You're trying designing this can. So what are the pieces that make up this can? There are 3 pieces. There's a top. There's a bottom. This is 1. This is 2. And then there's what? Then there's the can itself. Now, you have to be aware that we're looking for 2 different parts here. Because the can lid and the base, what formula are we going to use there? Not a cylinder, of a circle. So the area of a circle is what? And then we have everything else. We have the area of this region there. Right now, what we have here, we have the height. We have the area of both of these. But we can't really do that because that would give you a solid cylinder. Does it say we need to have a can? Now, what's not being stated there correctly, it does say 1 liter can. Cans are usually empty because they have to hold 1 liter worth of material. But the way it's looking like, it could also be a solid tube, or just a chunk, but that would be useless. We wouldn't be looking for the least amount of material. It would just be one amount of material. So we have to look for this has to be the circumference of it. And we'll look about that in a second. So what do we know? Are we looking for areas or volumes or what? Has to be a volume Why? Yeah, it has to be held. And what are our dimensions? What's our degree? The radius is squared. The radius is squared, so both of these together would be squared. And then we have this one. So we have to deal with volumes because it's cubic. Area is squared, base times width. Volume is base with height. So we have 3 dimensions. So here's the only part that we have to look at a conversion chart. Since the volume is equal to 1 liter, you can put it into any units you want to, but the easiest one would be 1,000 cubic centimeters. You can use deciliters or decimeters or hectometers or meters or you get all those, but the most logical, easiest one to deal with would be centimeters. So we know this conversion for the volume. So our volume that we deal with is pi r squared times h. And we know what? We know that this formula has to equal, since it's the volume, we also know it equals 1,000 centimeters cubed. So I'm just going to use 1,000 here. This is important. This is what we call our constraint. Remember in the last one we had a domain? This is in essence the domain of this one. Because this tells us where our boundaries. It cannot exceed 1 liter of volume. So what do we solve for here? What's our unknown that we need to define? Nope. Well, what's the formula for this one? We have the area of the circle at the top, it's the area of the bottom. What is this one going to be? Is it area or is it circumference? Remember, it's the outside of the can, not area. It's circumference because it's 2 pi r times h. Because we know the length here, remember, it was the outside of the can, which is 2 pi r, times the height. That's how much material we have in there. So we add these 3 together, it'll give us our formula. 2 pi r squared plus 2 pi r h. Well, I'm sorry, that's our area. That's our area. We need good. Now, we also know that this here, so what is the only thing we don't know here, because our functions are with respect to which variable? The radius. The radius converts everything. It'll change the area of each of these lids. It'll change the volume here. So the only thing that's really, what we have to do is we have to write we need h as a function of r. because we can only have functions of R here. So working with this, we have H is equal to 1000 divided by pi R squared. So let's take both of these formulas and put them together. Because all we want is one equation that is a function of R. So we know the area, let me write this right here. We have 2 pi R squared plus, 2 pi R H. We know H is equal to 1000 pi R squared. Put them together. We get 2 pi R squared plus 2 pi R times 1000 over pi R squared. Can we simplify this any? Yeah, the pi's gone. One of the r's are gone. So we have 2000 over r. So what's our objective now? We know our formula we're dealing with. It's going to be difficult. Yeah. I mean, we have to find r. What should I'll put it over here. We need to find an r that gives that maximizes the area. How do we do that? We're looking for the maximum of A. How do we find that? Maximum would be an extrema, right? How do you find extrema? First derivative, set it equal to 0. Remember, A is a function of R. So we're taking with respect to R. So we have 4 pi R. So we have here, we have plus 200 R to the power negative 1. Negative 2000 over R squared.
How did you get the 2000 over r squared?
Take the derivative. Take the derivative of this. Take the derivative of this. This one, we rewrite as that.
Yes.
Negative 1 comes down, you subtract 1. It becomes that.
Oh, okay.
So now we set this equal to 0. We set this equal to 0. We can move this over. We have 2000 over r squared equals 4 pi r. Because this is what we have to do. We have to do this. multiply both sides by r squared. So we have 2000 equals 4 pi r cubed. Divide by 4 pi. So r cubed is equal to 4 goes into 2,500 times over pi. To get r by itself, we cube root both sides. Does this function have any endpoints, any boundaries, domain-wise? Not really. I mean, 0, you can't have less than 0 radius, but there really isn't a maximum h, so it's just 0. It's no other endpoint. So, is this going to be a maximum or minimum? Since we don't have endpoints, to compare, how do we determine whether it is a max or a min? Very good. Exactly. Because now we'll take the second derivative of our function. So we have a prime is equal to 4 pi r minus 2000 over r squared. Find the second derivative and determine at that value if it's going to be positive or negative. All right, so here, let me write this again. A prime of r is equal to 4 pi r minus 2000 over r squared. Now we need the second derivative of r. The next derivative of 4 pi r is 4 pi minus 2000 r to the power negative 2. Bringing the 2 down. And r to the power negative 3, which makes it into 4 pi plus 4000 over r cubed. What do we know? In this equation, 4 pi is a constant, right? 4000 is a constant. What about r? What are our values of r? What's our domain of r? Can r be negative? Can you have a negative radius? Or r value, I should say? No. Can it be 0? Not really, because it wouldn't exist if it was zero. So R has to be greater than zero. Because R is greater than zero, this function is everywhere positive. This is positive. This is positive. So A double prime R is positive everywhere. So what does that tell us? It is concave what? If the second derivative is positive, it's concave up. So the value at R cube root of 500 over pi, is that what it was? Yeah. Will give us an absolute minimum. Let's see. Next one. Because it's everywhere positive, so that's our only extrema point. So partial good. Example 3. A rectangle is to be inscribed in a semicircle of radius 2. What is the largest area the rectangle can have? And what are its dimensions? So here we definitely have to draw a picture first to understand what they're talking about. It says we're going to have a semicircle, radius 2. So that goes from -2 to 2 and all the way up to 2. And inside there is a rectangle. So whatever this distance is, this is x, this is -x, has to be symmetric. And what are we looking for? So that's what the picture looks like. And we want the largest area. The area is length times width. So what is L? What's the length of our rectangle? Yeah, we have 1x there, 2x there, so it's 2x. So we're looking for this area inscribed there. That's what we're looking for. What is its width? Or actually, in this case, height. Let's do height instead. So how high does it go? Not 2. 2 is this length. That's that 2 length. What is this position here? This is where we have to do some math. This is where the algebra comes in. It's a semicircle, right? Of radius 2. This way we have to bring in everything that's given to us in there. A rectangle is inscribed inside there. We got that. That's what we got the length of. Now we have to define this outer equation. What's the formula for semicircle? What's the formula for circle? R equals x squared plus y squared. R squared equals x squared plus y squared. All right. What else do we know about it? What else did it tell us? Because it's centered at the origin. That's why it's not x plus h or x minus h, y minus k. Because the formula for a real circle is radius squared equals x minus h squared plus y minus k squared, where the center is hk. Since we're dealing about the origin, both cancel, so we have r squared equals x squared plus y squared. Okay, we know that. Here it tells us radius 2. So what's my radius? My r is 2 squared. So we get 4 equals x squared plus y squared. What are we solving for? We're trying to find the equation of this of that semicircle. So we solve for y. So y squared is 4 minus x squared. Square root both sides. Y is equal to plus or minus the square root of 4 minus x squared. Remember, anytime you square root something is squared, you have to put plus minus. But here is the but. It said semicircle. This would define the entire circle, the positive part above the x-axis and the negative part below the x-axis. All we want is a semicircle. So all we want is the positive side. So our formula is y is equal to the square root of 4 minus x squared.
How did you decide again for the plus or minuses to remove that minus?
Well, it said a semicircle, only half a circle. If it
So
was a
it's-
full circle, then it'd be plus or minus. Then we'd have negative parts also.
Oh, okay, so it's not like divided by 2 or anything.
No, because if this way, because here we have the equation, this would be y to be positive, and now y would be negative. Since we're doing only half a circle, we only want the top part, the positive part.
Okay, thank
Okay, this is our height. This is the formula for our height. So remember, we had length was 2x. Height now we know is square root of 4 minus x squared. So what's the formula for the area? The length times height, which is 2x square root of 4 minus x squared. Remember, this is a is a function of x. What's its domain? What's our domain? What's our bounds? How do you find the domain? Take both of these, set them equal to 0. So we get x equals 0. Get rid of the square root. You square both sides. So you have 4 minus x squared equals 0. 4 equals x squared. Square root both sides. So x is equal to plus or minus 2. Since we're starting at 0, we only go to positive 2. So our domain is from 0 to 2. And here's our formula for area of the function. Okay, we have everything defined. We have our domain. This is where x has to sit into. Cannot be above it, cannot be below it. Now what do we do? What are we looking for? We're looking for the rectangle. What is the largest area the rectangle can have? So how do we find the largest area the rectangle can have? How we solve the first two problems? What's the first thing you do when you look for extrema points? It's rib. I shouldn't have to give you those clues so explicitly. I'm telling you what to say pretty much. You should know what to say already because we're looking for optimization problems. Optimizations automatically means you're looking for the maximum or minima. Those are the extremas. So we're going to take a derivative of area. Two x times the square root of 4 minus x squared. So the derivative would give us, let's use the product rule. So f is 2x, f prime is 2, g is 4 minus x squared to the power 1/2. G prime is 1/2 4 minus x squared to the negative 1/2 times negative 2x. The 2's cancel. So we got negative x over square root of 4 minus x squared. So we have 2 times the square root of 4 minus x squared plus, but it's a minus, so it's a minus 2x times x over square root of 4 minus x squared. So 2x times x, so we have 2 times 4 minus x squared minus 2x squared over 4 minus x squared. What do we know about this equation? This is my first derivative. Do we have any restrictions? Remember, our domain earlier was between 0 and 2. What do you notice about this now? What value can you not use here? Yeah, so x cannot equal 2 because it'll make it undefined on the bottom. What do we do with this to find extrema? Set it equal to 0. Minus 2x squared. Move this value over here. So I have 2x squared over square root of 4 minus x squared equals to 2 square root of 4 minus x squared. Algebraically, what do you do next? Multiply both sides by the denominator, square root of 4 minus x squared. These cancel, so we have 2x squared square root of 4x minus x squared times 4 minus x squared is 4 minus x squared. So we got 2x squared equals 8 minus 2x squared. Move all the x's to one side. So we add 2x to both sides. So we get 4x squared equals 8. Divided by 4. X squared equals 2. Square root both sides. So x is equal to plus or minus square root of 2. Can we use both of them? This tells me where my extrema are. Right, because domain 0 and 2, we can only use the positive value. So we can only use that one. So we check x equals 0, x equals square root of 2, and x equals positive 2. So a of 0, a of radical 2, and a of 2. So a of x is equal to 2x square root of 4 minus x squared. 2 times 0 is 0, rest is 0. This would be 2 radical 2, 4 minus radical 2 squared. So 2 radical 2 times 4 minus 2, 2 radical 2, radical 2. Radical 2, radical 2 is 2, so it equals to 4. And then 2 squared is 4, 4 minus 4 is 0, so this is 0. So my extrema occurs we're looking for the largest area. The maximum area will be 4 at x equals square root of 2. We'll come back to the next one because it's pretty lengthy and it'll make us, we'll have to jump from algebra to trig to solve the next one. It deals with light refraction. Economics. We talked about this earlier. In economics, we deal with two basic functions, three actually. Cost, revenue, and profit. Cost is a value of production. Revenue as a value of production, and profit as the revenue of, as a function of production. The profit is the cost minus the revenue, or revenue minus cost. You can do it either way, or revenue minus cost. Let's be optimistic. So cost is C of X, the revenue is R of X, and the profit is R minus C. Now, to see how things change, the rate of change of our cost, of our revenue, of our product, we do marginal changes. So we have marginal cost is the first derivative of your cost function. Marginal revenue is the first derivative of your revenue. And marginal profit is the first derivative of your profit function. Because remember, the cost and revenue are differentiable functions because they're functions of X. They have to be continuous. You can't have cost that skips and revenue the same thing. It has to be continuous, so it's differentiable. Because they're differentiable, that means our profit function is also differentiable, which also means that since it is differentiable, it has a extrema. You can find a maximum if the revenue is much larger than the cost, and you have a minimum if the revenue is less than the cost. Let's look at an example here. And they say the best case scenario is when your cost and revenue equals the same, your profit is zero, but you're not losing money. So, that's what you have. That's your target. It's shooting at your target area. Example 5. Suppose R of X is equal to 9X. And C of X, your cost function, is X cubed minus 6X squared plus 15X. Where X is equal to millions of MP3 players produced. Is there a production level that maximizes profit? If so, what is it? So what do we have to find here? We're trying to find the maximum, right? An extrema. What do we have to do in order to find it? Why? Why would we do that? Yeah, but we're looking for the profit. I'm playing devil's advocate. You could be right. I'm just testing to see what you know. Because what would the profit function be? We defined it a second ago. Right. So the derivative, the marginal profit, would be the derivative of your revenue and your cost. So to break even, what do we need to know for sure? Let's find out what we need, the bare minimum. Okay, so what's R prime? What's C prime?
Squared. 18x. Yeah, minus 18x.
Right.
Oh.
Take the derivatives, bring the power down. It's quadratic, so it's set it equal to 0, which means I would subtract 9 from both sides. So we get 3x squared minus 12x plus 16. So what do we do now? How do we solve this one? What's that? We can't do a 3x. We can do a 3. We give us x squared minus 4x plus 2. Give me two numbers where you multiply, you get 2. When you add them, you get 4. 2 times 2 is 4. There's two numbers multiplied to equal 2. When you add them, you equal 4. There is none, so we can't use factoring. So we have to use the Pythagorean theorem. I mean, the quadratic formula. Where A is 1, B is -4, C is 2. Negative of a -4, -4 squared, minus 4 times 1 times 2, 2 times 1. Negative is a positive 4. -4 squared is 16. 4 times 2 is 8 over 2. Four plus or minus 16 minus 8 is 8. Eight breaks down into 2 times 4, which is 2 times 2. So the square root of 8 is 2 square root of 2 over 2. On the top, we can factor out a 2. And the 2's cancel. So my possible x values are 2 and -2. Are 2 plus radical 2, 2 minus radical 2. So what do we do with that? We're looking for economics marginal changes. Is there a production level that maximizes profit? So we're looking for a maximum function. So what do we know about our function? Is it increasing? Is it decreasing? Is what doing what? How do we know? We have to first look at the function itself. We're looking for profit. The profit of the function is r of x minus c of x. So r of x was 9x minus 3x cubed minus 6x squared, oops, plus 15x. Take the first derivative, let's just simplify these. P of x is equal to 9x minus x cubed plus 6x squared minus 15x. The first derivative is 9. 12x minus 15. And the second derivative is negative 6x plus 12. So what do we know about what to do with this? Second derivative tells us concavity. What's our domain that we're dealing with? So we're looking at between 2 plus or minus radical 2. Well, really, we can't use negative plus 2 plus minus 2 radical 2. If we plug that in there, what do we get? So we do the second derivative of 2 plus radical 2 and the second derivative of 2 minus radical 2. We get negative 6 times 2 plus radical 2 plus 12. Negative 6, 2 minus radical 2 plus 12. So negative 12 plus radical 2 plus 12. Those cancel, so it's just positive 2. Negative 12. Oh, that's minus. I'm sorry, that's minus. It's minus 6 radical 2. Plus 6 radical 2 plus 12. So it's negative at 2 plus radical 2. So we get a max at 2 plus radical 2. We get a min at 2 minus radical 2.
Shouldn't it be the other way around? Like if it's positive number, then it'd be
It's
the
concave up.
Oh,
If it's positive, it's concave up. That means minimum. If it's negative, it's concave down. It means maximum.
okay.
Since we're looking for the largest, we're looking for the maximizes. We want to know where the most occurs. So the most is going to occur at 2 plus radical 2. At P of 2 plus radical 2, whatever that value is going to give us. All right. That's the end of that section. Tomorrow I'll go through that one optimization problem of the optics. Because the next topic we're going to discuss, the last topic in this chapter, is called an iterative technique. Newton, it's what it does. It takes one value. You have to. This is the only time where you have to guess at something. You input it and you take it from there. So it won't start until you give it an initial guess, and then you progress it from there. And what it's going to do is going to localize to see how close and to what value the function is approaching. And that's what we call an iterative technique. We'll be using Excel for that. because it takes too long to use a calculator. All right, I'll see everybody tomorrow.